All right. So before we get to chapter 15, I want to spend a couple moments in chapter 2. Hold on. 2.3. This goes way back to the beginning of the course. This is it here. All right, here we go. So let me share the screen with you. All right. Now, this is a section of chapter 2 that we did not cover earlier. And this has to do with the relationship between two quantitative variables. So just like in algebra, when we wanted to look at the relationship between two quantitative variables, we created an XY coordinate system, right? Cartesian system. X was usually along the horizontal axis and Y was along the vertical axis. And then typically we would plot some points and then draw maybe a straight line through them or a curve through them. Now with data, we know data is messier than what we saw in algebra. You know, not all the dots fall on a straight line. Not all the dots fall on a curve, you know, on a curve like a parabola. So what we have to do in this course is to, number one, we want to plot these XY coordinates if we're comparing two quantitative variables to get an idea of visually what the relationship is between the two variables. Now, if we plot some points, and we all gone through this process before when we were in school, earlier school, and we see the, you know, the Y and the X coordinate here, and we see some dots that are plotted. If we see a trend, that is, these dots seem to be going up towards the right, then we might say that there might be, I'm not saying there is, but there might be a positive linear relationship between the variables X and Y, even though the dots do not fall directly on the line as they would in algebra. Algebra would be when we come up with our relationship, Y is equal to like 2x plus 3 or something like that, we're giving an exact relationship between X and Y. We're saying when Y is equal to 2x plus 3, that every point on the line, to get to that point from another point, what will we do? Well, we would plug in an X into that equation and get our Y. All right, and that tells us exactly where we are on that line. However, with this scatter plot, the points aren't exactly on that line, but what we're trying to do is establish some relationship between X and Y, which is an approximate relationship as opposed to an exact relationship. All right, and that's what this topic we're going to be talking about, regression, is all about. We're comparing quantitative, well, at least in the case that we're going to be looking at, quantitative variables, two quantitative variables. And number one, we want to see if there is a linear relationship, possible linear relationship. And number two, we want to establish what that relationship is, even though it's not an exact relationship. So if it looks like the dots are going up towards the right, we call it a positive linear relationship. If the dots seem to be going down towards the right, we would call it a negative linear relationship. If the dots seem to form a curved, instead of a straight line, a curved line, we call that a nonlinear relationship. That's one way of saying it, nonlinear. Or it may look like there's no relationship at all between all the dots, And therefore, the best line that fits that is a horizontal line. And if you remember, a horizontal line has zero slope, has no slope. All right. So we would say in this case, doesn't seem like there's any relationship between X and Y. All right. So that's the whole idea of creating a scatter plot. We can do it in our Minitab. So actually, I think, let me stop sharing this and go into Minitab. All right, and actually, I was working with Han this afternoon. Han had some questions about homework, and he actually came up with the dot plots of the. This was a homework problem way back when we did Chapter 2 homework, and I was showing how we could create these two dot plots on the same scale using Minitab. But what we could also do is in this case, is do a scatter plot of these two columns, the 1980 column and the 2007 column. I forgot exactly. Han, do you remember what these numbers represented for each state? Maybe not. I don't remember myself, but whatever that number is, it's the same. It's the same variable. It's the same variable, but we're just comparing it for two different years. So instead of doing the dot plot, we could do a scatter plot here of those two variables. We'll do graph, and the very first one is a scatter plot. And we just have to pick which one is X and which one is Y. Okay. Now notice here, you can get I don't know if it's true in the Mac version of Minitab, but in the PC version, you can get these other options, and besides the simple scatter plot, you can get one actually with a line that goes through it, which is the regression line, which is what we're going to talk about today. All right, this regression line here. Do you have that option, Steve? I know you have the Mac version. If you open up scatter plots.
Yeah, there's 5 options, just simple.
And do you have the one with regression? You have the one with regression also?
Wait, so you go to graph and then scatter plot, and that's what's there?
Yeah.
Okay.
How about you?
If I go to graph and scatter plot, it just has one Y variable where it's simple groups overlaid or groups displayed separately, and then multiple Y variables where it's overlaid or displayed separately. But those are the only options.
All right, there's nothing with regression. Okay, that's okay. I'm not going to ask you to do any of this. But if we just pick the simple one, which you can do, all right? And so you say, okay, and then you have to pick which your X and the Y is in this case here. So just for simplicity, let's make the 1980 to be your X. And all right, X is the 1981. And the Y variable would be 2007. All right, so we're just looking at the relationship. We're not actually doing much more than that. And then I'm just going to hit OK, see what it looks like. There we go. So if you look at the dots here, it looks like there is if you wanted to draw a straight line through this, it looks like it would be a positive linear relationship, right? It seems if you wanted to draw a line through this, you could. Now, so that's it for scatter plots. You know, you have two quantitative variables. You want to check to see if there's any relationship between them. Obviously, we could have, and this is just for demonstration. Obviously, Steve, you can't do this with your version of Minitab, but we're going to do it with this version here. I'm going to pick with regression. All right, and again, I'll do the same thing I just did a minute ago. And it'll be the same group of dots, but a line will go through it as opposed to, in addition to those dots. So it drew this line through it. Now the question is, why did it draw that line and not some other line, right? You could picture multiple types of lines with going through different points, going through maybe having different slopes, right? I mean, why this line? Why did it pick this line as opposed to any other line? All right. So that's what we want to talk about. Now, one thing that in this section 2.5, which is the section that we're looking at in the book, 2.5, it does mention that the x variable, the one that's running along the x-axis, we're going to call it the independent variable, and the y variable is called the dependent variable. All right. Now, if there was truly a causal, now this is the thing that what I want to bring out. Many times people will look into this because they think there is a causal relationship between x and y. In other words, x is causing y, right? So they may call x the independent variable and y the dependent variable because x is causing y. There doesn't have to be, in a scatter plot, a causal relationship. It could simply be what we're looking at here. We're just seeing if there seems to be any trend. As x increases, does y increase? As x decreases, does y decrease? That sort of thing. All right. It doesn't mean necessarily that x is causing y, which it wouldn't in this case. All right. There's no necessarily causal relationship between these two variables. But that's where the terms independent and dependent come from. When you read chapter, and I would recommend reading section 2.5 in the book, that's where those terms come from, independent and dependent. It implies a causal relationship between the two variables. Well, the section's not very long. It's only a couple pages long, so it won't take you long to do it. But it does mention in section 2.5 that there is a what they call a best fit line or best fit equation. Obviously, a straight line has an equation with a slope and y-intercept. Almost every person who's been through high school seems to remember y is equal to mx plus b, right? People remember that, where m is the slope and b is the y-intercept. When you went through your schooling, I don't know if you weren't in the U.S., right? You didn't go through high school in the U.S., is that right? Han? Are you there?
No.
Okay.
No.
All right, but does that still sound familiar to you when we say y is equal to mx plus b?
Yes.
Okay, good. So there must be a universal language. All right. So they talk about a best fit equation, and the question is, what does that mean? Why is this line, which I'm assuming they call it the regression line, why is it the best fitting line as opposed to any other line that we could have drawn through these points? Okay. And that is the topic of chapter 15. Chapter 15 is all about that. All right. So, chapter 15 is just an introduction. I have to really tell you that to learn regression, it takes probably years to learn it because there are so many different types of regression models. We're going to call them models. And there's so many ways of doing regression. In Minitab, for example, if you go to stat, regression is the second choice in your menu here. And if you just move your cursor down, you can see there are many types. And these aren't all the different types, by the way. This is just what Minitab is put on here. I have another program where the list would literally go to the bottom of the page. All right, there are many types of regressions. Now, what you're going to be learning is the simplest type, because to learn what regression is, you have to start with the simplest case. All right. And the simplest case is going to be where the x there's one x variable called quantitative, and there's one y variable which is quantitative. And even though I told you a minute ago that we're going to assume that we cannot assume that there's a causal relationship between x and y, the regression model does imply that. It does imply that causation. Okay. Let me just check one other thing here. in the book. Just give me a second. Now, chapter 15, and I think beginning students, now you guys aren't beginning students, but many beginning students, I mean real beginning students, people who've never taken anything like this before, will start getting confused a little bit from the get-go with this, because on the one hand, we're going to say the relationship between X and Y, we have a quantitative measure of that called correlation, which we'll get to in a minute, which does not imply causation. And then we jump right into regression, and then we're going to say, oh, there's a possible causal relationship there. That's why we do regression. All right. So students immediately get confused. I think they probably, maybe they can't articulate it, but I'm quite sure they're immediately confused and they're lost probably, except for the steps of what they need to do. But in terms of understanding it, I think they get completely lost. So I'll try to avoid that tonight if I can. So we'll go back to the book, and we're going to go to chapter 15 now. All right. Now, by the way, before we go to chapter 15, these curves here that we're displaying, the concept of correlation, which we'll talk about in a minute, depends on there being a linear relationship between the two variables, two quantitative variables, a linear relationship. And as you'll find out, correlation, the way it's calculated, does not have any units of measurement. They're kind of canceled out. So when we calculate, see, X and Y have their own units of measurement, but when we calculate correlation, they get canceled out. They're gone. And what's left is something that has no units. But it does have a range of values. Correlation is from -1 to 1. So what's -1 represent? And this is why, and the reason I'm bringing it up, because these graphs are conveniently here. A -1 relationship between correlation between X and Y would be where you have a downward sloping line that goes through these points, and every single point is on that line. It's called perfect negative correlation. That you'll never see it with real data, all right? But it exists because in high school, when we learned algebra, we drew a line and every dot was on that line. So that's called perfect correlation. And when it's sloping down, we call it perfect negative correlation. And that would have a correlation equal to -1. On the other hand, if we have a positively sloped line, best fitting line, and every one of these dots were on that line, if you could picture that, that would have a correlation of +1, and that would be called perfect positive correlation. So every case that we're going to look at is going to be between those two extremes. Those are two extremes you'll never see in real life. And basically, the stronger the correlation is between two variables, the closer the correlation number will be between -1, will be to either -1 or to +1, depending on whether it's negative or positive correlation, okay? The closer the number will be. So for example, -0.9 would be a case where all these dots are really close to the line, but they're not necessarily on the line, but they're close. And it's no doubt about it that we have a negative linear correlation going on, right? Negative slope, and all the points are hugging that line, but they're not on the line, but they're really close to it. And then maybe this case here that we're looking at might have a 0.7 correlation because the points are more scattered around the line. And then the case that we saw in Minitab just a minute ago when we did a scatter plot, the points were even more scattered. And we would say that the correlation was not as strong, but it still would be positive, right? We could picture a positive trend. So The more scattered the points are around the line, the weaker the correlation. All right, I hope you can picture that. The closer the points are to the line, the stronger the correlation. The correlation actually has two components. It has, typically when you define it, it has two components, strength and direction. Strength indicating how close the points are to the line, the best so-called best fitting line, which I haven't defined that yet. And secondly, the direction. Is it directed up towards the right, which makes it positive? Is it directed down towards the right, which makes it negative? And the sign of correlation matches the sign of the slope. All right, the slope of the line, if it's positive slope, it would be a positive correlation. Negative slope, negative correlation. Now, here's the thing. We just talked about these two graphs here. How about this one here? The curved line. One's where it's really, where it looks like it's more of a curved relationship. Because correlation measures linear relationship between two quantitative variables, this curve, this shape here would have a correlation close to 0. Even if every one of these dots was on this curve, it was perfectly curved, right? Relationship, it would have a correlation of 0 because the correlation measures a linear, not a nonlinear relationship. You have to remember that. All right, it measures a linear, not a nonlinear relationship. And actually, these two cases here would have correlations very close to each other, which is close to 0. This one, the curved relationship, and the one where there's no relationship. And that's why if you see a correlation close to 0, it's very good to do a scatter plot, because then you could see which of these two cases it is, whether there's a curved relationship or whether there is simply no relationship at all. Okay? Mm-hmm. And that's important, because if it's a strong curved relationship, then you have to think about doing some other type of so-called regression where you can actually have a best fitting curve that goes through the points. All right? The correlation by itself only measures linear relationships, and that has to be remembered when we go through the process of doing regression. All right, does that make sense what I just said? I hope it makes some sense. Okay.
Yes.
All right, now chapter 15, we're going to go into chapter 15. We're skipping actually chapters 12 through 14, right? Which would be more like, would be in a Stat 2 course. All right, those chapters are more in Stat 2. It is unusual, by the way, to see linear regression occur after these, but that's the way this book laid it out. So let's go to chapter 15, go to the introduction to it. All right. And once again, they introduce you to some, the idea of a dependent and independent variable. Okay. And for example, now, remember, correlation it only measures the strength of the relationship, and this is a mistake. This is not a complete understanding. It measures the strength and direction of the relationship. The newer books mention both of those items. So correlation analysis does that. Remember, correlation analysis does not imply causation. However, when we do regression, we are implying causation. All right. The regression does not prove that the X is causing the Y, but it gives an indication maybe that it does. Now, here are some examples of causal relationships. For example, we might think that advertising, the amount of advertising that we do in a company affects the amount of sales that we get, the dollar amount of sales or the number of sales, right? You may think there's a causal relationship, and we want to see if that's true. We might think that somebody graduating from college and applying for a job that the higher their grade point average is, the higher the starting salary is. Well, we wouldn't need to see if there's, see if there's a relationship. Now, it's possible there's not a causal relationship, right? It's possible there could be factors that influence both of those simultaneously. The quality assurance expenditures, what does that mean? It means the amount of money a company is willing to spend making sure that the products that are going out are defect-free, right? We would think that the more money we spend on that, the fewer the product recalls would be. We would anticipate a negative relationship there, right? More money spent on quality assurance, the smaller number of product recalls, but we would have to test that out. Circulation of a magazine determines the cost of a magazine ad. All right, how much is the circulation? Well, that sounds like it'd be kind of a significant thing, right? The more circulated the magazine is, or even in today's world where it would be online circulation, it would be we would think the cost of an ad would go down, right? The cost would go down. So we would think there's a negative relationship there. But regardless, these are the types of questions we can ask, and then we use data to determine if there is a relationship. And again, in the beginning, we're looking at linear relationships only. All right. All right, so let's go to the next section, and we're going to look at this new model called the simple linear regression model. Now, the word simple is put in there because it is the simplest case where the independent variable x is a quantitative variable, and we only have one x. We anticipate, for some reason, we anticipate that there's only one variable that can influence the so-called dependent variable y. All right, there's only one causal mechanism. That's x influencing y, and there's nothing else. All right. So that's called the simple linear regression model, and both x and y are considered quantitative, and there's only one x. Now, in today's world, when you do regression, I don't care what kind of regression you're doing, it will be what's called multiple regression, where there's more than one x. And again, there's people doing models in today's world where there's hundreds of x's. There could be, right? There could be lots of factors influencing y. Anyway, so we're looking at the simplest case, simple linear regression, and we're going to look at it and determine a linear equation, just like y is equal to mx plus b. One linear equation with one x and one y. Okay, so there's going to be a y-intercept and a slope. All right, and here's the deal. Again, like we saw in the scatter plot, the x's and y, the xy points are not going to fall directly on that line. And the question is, number one, why did we pick that line? And number two, how do we find it? Okay, so that's really the first questions here. Now, the model is going to look like, if you have your book open, I don't know if you can see this very well here. This is the model here. All right, this equation here. It looks kind of complicated, but let me explain it to you. All right, it says y, and it has a sub I there. That's an I. All right, I is equal to b sub 0 plus b1 times x I think that's an I, right? I plus this Greek symbol, that's epsilon. That's epsilon, by the way, for those of you who are interested, with an I next to it. Yi is a value of the dependent variable y. So this is basically, the I represents what? The I represents one possible value of x and y. All right, one possible xy pair. All right. So there could be, if you remember in algebra, if we were graphing points, we might call one of the points x1, y1. We call another point x2, y2. Remember that when we went through that? The same thing here, but we could have many more points. We could have 100 points, and each one of them would it be x1, y1, x2, y2, like that, all the way up to x100, y100. So x represents a value of the independent variable x. B sub 0 is the y-intercept. It just doesn't look like the equation that we're used to seeing. But it's called beta. Beta. It uses the Greek letter beta. And they put a little 0 in there for what reason? Because it's the y-intercept. It's where x is equal to 0. Okay? Now, by the way, when we're doing real data, there may not be an x equal to 0. All right? We might be plotting, for example, x might be income, for example, yearly income for somebody. And all the points that we have are all non-zero numbers. All right, and we're looking at the relationship between income and maybe the size of the cost of the house that they live in. Maybe that's possible, right? Something like that. We want to look at that relationship. Well, if we say somebody has no income, well, it's possible they may have a house, but it might not be very likely they have a house if they have no income at all. So the y-intercept is there in many cases just to make the equation work. It may not actually have a practical meaning to it. That's really my point. It could have a practical meaning. It may not have a practical meaning. B1 represents the slope of the regression line in this equation. It's the slope. Epsilon I is called a random error or residual. That's the term that statisticians usually use. Instead of calling it a random error, they call it a residual, or something that's left over. That's what the word residual means, something that's left over. So why do they put that in the equation? Because there is, the line is not a perfect relationship between x and y. The line is an approximate relationship, and therefore there may be some error. Not maybe, there is some error that's going to be formed when we use this line to approximate the relationship. There's going to be some error there, and that's that so-called residual. Now, how is it defined? How is it defined? Well, if we actually have the x and y points, picture having, let's go back to, let's go back to Minitab for a minute. This is the advantage of actually having Minitab here. Actually, they use it for teaching, which is nice, instead of just, so let's look at these points here and look at the line that goes through it. So the residual, let me describe what it is. It is the vertical for each one of these points. And there's many points here, right? There's 50 of them, right? Because there's 50 states. There's 50 points that are here. For each one of these points, each point here will have what's called a residual. The residual is the distance from the point to the line. It's the vertical distance from the point to the line. Remember, the line is an estimate of this relationship. All right, and I'm going to explain how this works in a second. Notice this point right here is very close to the line. And the way we calculate residual, it's literally the height or the y value of that point minus the y value that is on the line itself. Okay, does that make sense? That distance, therefore, if the point is above the line, it would have a positive residual. If the point, like this one over here, is below the line, it would have a negative residual. So some of the points are going to have positive residuals, all these points. Here's a point here that has no residual because it's right on the line. And then all these points below the line have negative residuals. So it's the vertical distance between the point and the line. The line is the predicted value of y given that particular value of x. It's the predicted value. Does that make sense? It would be predicted, right? Based off of the use of that line. But the actual y is where the actual point is located for that value of x. Now, not every value of x is represented here. Some values are and some values are not, okay? So this line here could be used to predict if we have a value of x that's not used in these 50 here, right? These 50 values, we could use the line to predict what y is based on the equation of this line, right? We could simply take the equation, plug in the x, and get our y. And that would be the predicted value of y given value of x. So we could do that, right? There's no need to do it for points that we already have. For the x's that we already have, we know the value of y. But anyway, so we have all these residuals, some positive, some negative, some zero if they fall right on the line. So the question is, why this line here? Well, here's the definite. Now, another thing we could do, let's say we wanted to have some measure of these residuals in total, not just one of the residuals, but all 50 of them. What's one thing that we could do? One thing we could do is take each of the residual values for each of these 50 points and just simply add them up. Maybe take the average of them if we wanted to. Add them all up and divide by 50, and that would be the average residual. But what we'll find is if we added up all the residuals here, it would equal 0 or very close to 0, maybe some rounding error, but basically 0. And that's not very helpful, right? A summary measure equals 0 doesn't really help us at all. And the reason for that is that the positive residuals and the negative residuals are literally canceling each other out, and we're left with 0 when we add them up. So just like we did in the concept of variance, where we wanted to measure the variability of data, and we found that if we simply took the deviation from the mean and added them all up, we would get 0, right? What did we do back then? We squared the deviations from the mean. And we came up with this idea of variance. We averaged that and we came up and we have variance. We're going to do the same thing here. We're going to square each of those deviations so that the positive ones stay positive, the negative ones become positive. All right. So we eliminate all the negatives from the relationship. And so we're going to add up all the squared deviations. Not squared deviations, squared residuals. We're going to add them up. Now, here's the definition of the best fitting line. When we add up all the squared deviations, the line that produces the smallest sum of the squared deviations is the best fitting line. And doesn't that make sense? Because the residuals are measuring the error for that particular point. How far away is it from the line? We square these errors up and add them all up. Doesn't it make sense we want the smallest errors, right? We want those points to be the closest to the line. That's literally what we're doing. We're trying to get those points as close as we can to the line that we want. The one that produces the smallest squared residuals is called the line of best fit. And if you've taken calculus before, you can use calculus to do this. All right, Steve, did you take calculus that way back when? Yes, and Han, did you take calculus? Ever take calculus?
Yes.
Yes. So there was something in the beginning days of calculus where we would find the we would take a derivative and set it equal to 0, and if this and we would look at the second derivative, that sort of thing, and the whole idea was it to find the minimum or maximum of something. Remember,
Mhm.
This is a minimization problem. It's exactly done the same way. We use calculus. And what happens when we do that calculus, which I won't go through, it's unnecessary for this course, is we will end up with an estimate for the two um, not variables, but two parameters that are in this model. So let's go back to the book again. And what are the two, let's look at this equation again. What are the two parameters? It's beta sub 0, the y-intercept, and it's beta 1. And there's actually equations for simple linear regression for both of these. You can calculate both of them. And the whole idea is that I think you have to do one of these first, because you have to, and what happens is when you use these equations, you will have your estimate for the slope and the y-intercept, all right, in this model. And you just plug it into the equations, right? So calculus gives us the procedure for estimating beta sub 0 and beta 1, the y-intercept and the slope. And we end up with our best fitting line, all right, using the minimization procedure of calculus. This is called the least squares regression line. That's why they call it the least squares regression line. Now, if you ever take more advanced courses in statistics, you're going to find that there's a few other types of ways of doing this, especially when we get into more complicated models, where least squares doesn't really work as well. And you'll learn those at a later time, which way beyond this course. But that's how we come up with this equation. All right. Now, how is this done? Calculus, and this is the remarkable part of it. A TI-83 or 84 calculator can do this. It does the calculus for you. Any high school student now can literally use their TI-83 or 84 calculator, put in a data set, all right, find the correlation, and also calculate the line of best fit without actually doing anything. The only thing they're doing is putting in the X and Y columns into their calculator. And they end up with the line of best fit. Obviously, Excel will be able to do this, all right? Minitab, obviously, and any reasonable program can do this now. It's pretty easy. Now, once we put in the betas, we drop the epsilon from the equation, all right? Because now we have a model of prediction. We have a model of prediction. If we leave the epsilon in, what we're really saying is that there's some random error there. But if we're actually going to put a prediction model in there, we're dropping the epsilon. And what the epsilon, the reason we're doing it is because the expected overall average of epsilon is going to be 0. So literally, when we create our line of best fit, the epsilon is going to drop away, and the y is going to be an expected value. Remember the term expected value from probability? Did we talk about expected values? Well, that's what it is. We take the expected value of this equation here, all right? The y becomes what? It becomes a predicted y. And then we have an estimate for B0. We have a beta 0. We have an estimate for beta 1. And the expected value of epsilon is 0. So that just sort of drops away. And we end up with our line of best fit. Okay? Does that make sense? And actually, if you look down here, if you did some algebra and you wanted to solve for epsilon, you simply subtract these two terms from both sides, and you end up with yi minus beta sub 0 plus beta 1 times xi. That's our residual. And doesn't that make sense? Because yi represents the true value of y, right? That is that real dot that's really there. And this equation here represents the line of best fit, this part of it here, all right? So this is the residual equation right here based off the original equation. All right, now they use some fancy things here. When they do the expected value of both sides, expected value of y, and then the expected value of the right side of the equation, they use this mu y dot x. I've never seen that in an introductory textbook. They don't do that anymore, all right? Most students would look at that and like say, I'm not reading that, I'm done. But what they're really saying is it's the mean of y given a particular value of x. This equation predicts that. All right, if we have an x at a particular value, we had a particular value of x, xi, all right, and we plugged it into this equation, we would have this, that would be the mean of y given that particular value of x. That's what that is saying there, all right? And this is way, in my view, a little too advanced for a beginning student, this notation here. But I think you guys hopefully will understand it. Now, there are 3 assumptions underlying this model. This is what you do need to remember. One assumption is that for each value of x, picture this, for each value of x, the y values are normally distributed with a mean that is on the regression line. In other words, this mu y dot x here, picture for a particular value of x that we could have that the y is normally distributed, all right? We could have multiple y's along a normal curve for that value of x. So that's one of the assumptions. So you can picture for each value of x, a tiny little bell-shaped curve drawn on there, all right? Number 2, regardless of the value of x, the standard deviation of each of the y values about the regression line is the same. So picture, again, having multiple y values possible for a particular value of x, all right? The variability of those y values for each value of x should be about the same. There shouldn't be any major differences as you move from one x value to the next. When we have this, this is an assumption of equal standard deviation for each value of x. Standard deviation of what? The y's, possible y values. And they use this very fancy term here, homoscedasticity. I've seen this term for many years. I still can't pronounce it without my tongue getting all wrapped up in my mouth. Homoscedasticity. The opposite of this, where the variability changes, is called heteroscedasticity. All right. There are measures of this. You don't really need to. It's too advanced. This is something that you go into if you're in graduate school. Now, Steve, you already have a degree, so a PhD, so you've been through graduate school. But when you
Never encountered that though.
what's that? What did you say?
Never encountered that though in my grad schooling.
Oh, okay. You didn't take a statistics course in grad school? I guess you did.
No, that's why I'm here.
That's why you're here. Okay. All right. Homoscedasticity, and I don't even know if I'm pronouncing it right anymore, just means that the variance for each value of x, the variance of y for each value of x, is going to be approximately the same. Again, there are charts that you can, graphs that you can create that will test for this. And there's also numerical measures that you can test for it. If you don't have this, if this condition is not met, you have to do something about it, all right? You have to modify the model, so to speak. And that's, again, beyond the scope of this course. The third assumption is that the y values are statistically independent of one another. All right, that's assuming what? That's assuming that the observations, I mean, let's say you have, in the case that we were looking at with the 2 years, right? We would have to assume if we were going to create linear regression model, we'd have to assume that the 2 years were independent of one another, that one did not create that. Oh, no, let me rephrase that. We would have to assume that each state was independent of one another. The Y value, the 2007 value of Michigan had nothing to do with the 2007 value of Pennsylvania. All right, they were independent observations. That's required, is that the observations are independent of one another. All right. There's actually a fourth requirement. We want, if we can, we want the independent variables. Now, there's going to be always some, if we had more, actually, the fourth requirement is only for if we had more than one X variable. So now that I'm thinking about it, you wouldn't see it here. But if we had more than one X variable, we don't want the X variables to correlate too much with each other. Does that make sense? We want them to be sort of separate from each other. There's always going to be some correlation between the X variables. So if there's too much correlation between the X variables, that's a problem also. And that's called multi-collinearity. But we're not going to see it here because there's only one X variable. All right. One X variable, we don't have that issue because there's no other X variable to look at in terms of correlation. All right, so these are the three that are assumed for the simple linear regression model, and all three have to be satisfied. All right, now you might say to yourself, all right, which one of these which one of these cases tends to be not satisfied? And that it's hard to tell, but number 3 is the most significant one if it's violated, because if the Y's are not statistically independent of one another, if they're not independent, then this model is not going to work very well. All right, you're going to get biased results for your beta and for your beta variables. All right, you're going to get biased results. They're not going to come out right. When does this happen? Well, what if we had the same person being measured for something over multiple time periods? Those time periods are not independent of one another, right? It's the same person. Mm-hmm. So you can't use this model for that. You have to do something. You may have to subtract their values or do something to get rid of that dependence between the observations. So there are many cases where you don't have statistical independence, and then you have to come up with another model. But we're going to assume that for this case here, the simplest case, that the observations are independent, and then we're good. By the way, here's a picture of that normality assumption. Here's a value of X, and here's the normal distribution of the values of Y that could happen for that value of X, all right? Because the value of Y that we got is just one possible value for that value of X, right? It's possible that we do another random sample and we'll get a different value of Y for that value of X, right? It's possible. And actually very likely, right? In this case, it's very likely. So we're assuming that the Y's are normally distributed for that value of X. So that's what all these normals are representing here. For each one of these X's, we're assuming that the Y's are normally distributed. All right. So that's one of the assumptions. Okay. So once again, the beta 0 is the y-intercept. It's the value of Y when X is 0, right? Again, it may have a practical value in the problem that we're looking at, or it may not. Beta 1 or B1 in this case here is the slope of the regression line. And then in this next section here, they talk about the least squares criterion that I mentioned to you. They use here they call it the sum of the squared deviation between y's and the scatter diagram. Again, just say the sum of the squared sum of the squared residuals. Now that we know what a residual is, right? Instead of calling a deviation between the y's and the scatter diagram, I don't think that's very clear, right? I think most people would be scratching their head wondering what does that mean. I think if you just say that the y, the actual y minus the y that would be right on that line, and it's called a residual, we would say the sum of the squared residuals. The equation must be that the sum of the squared residuals is minimized. All right, and again, we do that through calculus, right? All right, and then they go through a picture similar to what I was showing you before. Here are the two equations. Once we use our calculus, our minimization problem, here are the two equations that we end up with. All right, and I actually went through and I took statistics in graduate school. They asked us to do this as an exercise using calculus, because my statistics program assumed that you took calculus. It's a calculus-based statistics program. So this is one of the first exercises was to, in our in one I think it was the regression course, is to actually go through that exercise and do the minimization. And what you come up with is, number one, you have to come up with the slope first. And the slope comes up with this formula here. It's the sum of the product of each x and y. Each xy point, you're multiplying the x and the y values, and then you're adding them all up, those products. Minus n, which is the sample size, times the mean of x times the mean of y. So that's the numerator of the slope formula, and the denominator would be you take each of the x's and square them individually, square the x's and add them all up. That's what this means here, the sum of the x squares minus again the sample size times what? The mean of x squared. The mean of x itself squared. This whole calculation here, it comes out to the slope. Now, you could take an Excel spreadsheet, all right, and easily confirm this because the Minitab, for example, will give you the answer. Excel will give you the answer too, what the slope is. But you could do the x and y's and simply set up Excel to do all this math in here, right? You know what n is. You can figure out what the mean of x is, the mean of y. You can also set up another column where you're multiplying across the x's and y's, so you end up with your xy values and you add them up. You could also set up another column and square your x's and then add them up. Okay, and you can figure this out pretty easily in Excel. Now once you have your slope, you can calculate your y-intercept using this formula. Again, this formula comes from calculus, the minimization problem, and it's simply the mean of y minus b1, which is the slope, times the mean of x. Interesting, isn't it? That the y-intercept is the mean of y minus the slope times the mean of x. Okay, and that is the two formulas that come out when you actually do the calculus. You come up with these two formulas. Now, these graphing calculators, Minitab, any statistical program does all of this. It's programmed right into them, wired right into the program. So you don't have to do this, but I think it's an interesting exercise to actually do this once, not the calculus part, but to actually use the formulas once to calculate both the slope and the y-intercept, and confirm it, and confirm that it's equal to what the Excel or the program is actually telling you the answer is. All right, do it once just so that you get a feel for it, and then you'll never have to do it again. Now, when I took statistics in college, long time ago, undergraduate, I think I took it in 1971. That shows you how long ago that was. There was no calculators. Calculus didn't exist at that time. They had slide rules. I hated slide rules, so I never used them. So basically, you did all this by hand. You did all this by hand back then, calculated all by hand. So we had to do it back then. But I think, again, it's an interesting exercise to do it using Excel maybe, and just so you get a feel for it. All right. I mean, if you do this as an example here, come up with a regression equation where X is a dexterity score and Y is the number of units produced in 1 hour. I guess the more dexterous you are, dexterous means the ability to use your hands well in a task. So people with higher dexterity scores should produce more units in an hour. That's the whole idea, I think. So you could come up with a regression line using those formulas by simply putting this into an Excel sheet and then calculating the X times the Y, that would be one column. Squaring the X's, that would be another column, right? And then finding the mean, finding the sum of these things, finding the mean of X, mean of Y, simply then plugging it into the equations, and you should be able to get the answer, all right? And in this case, the slope is 19.2, and the y-intercepts, the slope is 3, and the y-intercept's 19.2. Notice they put a little hat above the y, because that indicates that this is an estimate, all right? An estimate. All right, we used that hat, remember, when we were doing recently, when we were looking at proportions, right? We used a P to represent the population proportion, and then for the sample proportion, which is an estimate, we put the little hat above it. And that's what they're doing here. They're putting a little hat above the Y to differentiate from the actual Ys that are in the data set. Okay, so basically, Y minus Y hat for each value of X would be the residual. So if I ask you, for example, if you had some X's, right, and I ask you to calculate a residual for one of those X's, you would simply put in, you would have your Y for that X, right? And then you subtract, and then you would simply put the X into this equation here to get your Y hat. That would be your value of Y that's actually on that line. So Y minus Y hat is the residual. Okay. Any questions about that? Okay. So this, again, basic terminology for doing all this. Here again is an example. I think they just showed you in this little problem here how to do it if you were going to do it in Excel or by hand. I guess this was maybe Excel, I don't know. But you would put in for each employee their X's and their Y's, and then you would multiply the X and Y's, you would square the X's, you would square the Y's. I guess squaring the Y's is required in the equation. No, I don't know why they squared the Y's. They didn't have to do that. Because I don't think sum of squared, no. So that was not necessary, was the squaring of the Y's. All right, didn't have to do that. They did it anyway. But basically, these two columns were good enough. You'd have the sum, if you added all these numbers up here, you have the sum of X times Y. If you added up these numbers here, you have the sum of X squares, right? You have the sum of X, sum of Y, and then of course, if you divide each of these by 5, you get your means also. And then you just plug it all in and you get your slope. And then once you have your slope, you plug it into this equation along with you plug it into what equation? The y-intercept equation, this here. You have both your the mean of X, the mean of Y, and you have your slope, and you get your y-intercept estimate. So there's the line of best fit. And that's why it's used as opposed to any other line, because it minimizes the sum of the residual squared. And it's used for estimation or prediction. Yeah, again, if you have an X that's not in the data set and you want to predict the Y, you simply plug in the X into this equation and you would have your value of Y that's predicted based on that equation. It is, I don't know if it's mentioned here, but it is typically mentioned that when you do prediction, you don't want to go outside of the range of values of your X's and Y's, or X's. You don't want to go beyond the range of values of your X's, because this equation assumes it's calculated only from these data points, not from other data points that are outside of it. Just these data points are being used for this equation. So it wouldn't make too much sense to pick an X that's outside of the range of these X's here. These X's run from a little bit less than 11 all the way up to a little bit more than 17. All right. So you don't want to predict an X that's maybe 5, or predict the Y for an X that's 5, or a Y for an X that's maybe 20, because it's outside that range. And we don't even know if this relationship continues beyond the range of X's. So we want to make sure that our predictions are always within the range of the X's that are in our data set. Any questions about that? So far, so good? Am I doing a good job? Say yes. Good.
Yes.
Yes, I'm doing a good job. All right, anyway. And then here's an example where you can estimate the Y from the X by just simply plugging in 15. Now, here, they're doing exactly what I said you should not do. Well, actually, you could do it. You could do it. Here's an X that's 15 is in the range of values of the X's, right? Again, it goes from a little bit less than 11 to a little bit more than 17. 15 is in that range, so it's legitimate to use this equation to estimate a Y based off of X is equal to 15. In this case, it would be 64.2. And where is the fall? It would simply be, you just run your cursor from 15 all the way up to the line, and that point on that line should be 64.2. Pretty easy, right? We did this, everybody did this in high school. Well, we always plug in an X to get our Y, right? Once we have an equation. So same thing here, but in this case, it's an estimate of Y would be, because we have no idea. We really don't know what the Y could be, because remember, it's a normal, right? A normal. So the estimate is one possibility out of that normal curve for that X. We're predicting it, and we're predicting it based on what? That line. So picture for X is 15, picture that, again, one of those normal curves around it. Where that normal curve intersects this line would be that value of Y. Okay? Picture that? Yeah. All right.
Mm-hmm.
Yeah. So that's it. So that's what they mean by point estimate. They're estimating the Y given a value of X that's inside the range of the X's. And again, they show you how to do it in Excel. All right. And again, this shows you the procedure for doing. I'm not going to go through the examples yet. I want to give you the background for all this first, all right? Before we, yeah, so we're almost done anyway. We've been over an hour. And, again, Minitab, there's a linear regression report, which may look different than it did 11 years ago. Remember, this is an old textbook, or 9 years ago. So this may not even be the way it looks like now. We'll have to look at it. I'm sure Minitab's going through several different iterations since then. See if there's anything else that I need to talk about. Interval estimation using a simple regression on that. I think that's a signal that we should stop right now. So I think that's a good introduction to linear regression. I think you get the idea of what we're trying to accomplish with it. All right. Again, hold on a minute. what we're going to do next time is just continue a little bit more, and then we'll start doing some problems with it, all right? And using Minitab to show you how to come up with solutions, all right? So we'll continue next time. I don't want to give you too much at once. Obviously, we haven't covered correlation yet, so we're going to cover that next time also, correlation. All right. It is highly unusual, by the way, for them to talk about confidence intervals in this chapter. So I'm a little bit, I think I could probably talk about that. There's also another thing called what's called the coefficient of determination. It's something, I think it's not harmful to talk about it here because it'll be part of the printout that you're going to get from Minitab. And I'll explain what that means also next time. Coefficient of determination. And then we'll do some problems. We'll start doing problems. And then so that'd be next Tuesday. And next Thursday, we'll wrap it up. We'll wrap up the regression in chapter 15. It's just an introduction, bare minimum. There's so much more to regression. Again, years of study, literally, before you think you can master regression. And then somebody comes up with something new, and then you realize you don't know very much anymore. So regression is a, this is just know that it's just an introduction for you guys, all right? But it's a good introduction, I think, because again, I'm such a wonderful teacher, all right? All right. So I'll see you next time, all right? I'm going to stop the recording unless you have some questions. And what I'm going to be doing tomorrow, starting tomorrow, is laying out a schedule for the things that you'll be doing at home, such as the homework. I'm going to be laying out homework for both chapters 9, 10, and 11. I probably should give you homework for this too, but I'll do that later. And obviously, I'll need to give you quizzes too. And then, so those things will be laid out. One thing I was actually thinking of doing for regression is maybe, again, I'm not saying I'm going to do it because it's time limits, but I might give you a little mini regression project to do using Minitab, where I'll give you a data set and then I'll ask you some questions and you'll answer them and then send back the results, that sort of thing. So that might be instead of doing a quiz on regression, give you a little project to do. That might be more valuable than giving you a quiz. All right. So don't worry about all that. I'm going to be starting laying that out tomorrow. Nothing will be due next Tuesday, but I will start giving you things to be done starting next Thursday into the weekend before you actually need to take your test the following week. So I'll look for my emails. I'll give you some emails, but definitely not next Tuesday. Maybe Wednesday. I could make it Wednesday or Thursday for the.
Okay, but you will email us about it tomorrow.
Oh, absolutely. Yeah, I'll start emailing you tomorrow, and I want to lay it out so that you can do it. All right. I don't want to, say everything is due, the Sunday before your test. That would be ridiculous. I'm not going to do that. All right. So that's it for today. Go ahead. Yes.
I have a question.
Yes.
Will the test cover the regression?
Yes. Yes. It'll cover regression too. Yes. But again, this is just an introduction, so it's not going to be complicated. Once you know how to do it using Minitab, it'll be a cinch. All right. And maybe you don't think so, but it will be, because I'm not going to, I won't have you do a regression during the test. I will ask, maybe I'll give you the printout and I'll ask you questions about it, something like that.
Okay.
That could be an exam question. Here's a printout, and I could, you don't know what the questions are yet, but I could ask you 4 or 5 questions based off of the printout. All right. So don't worry about it, because I'm not going to ask you to do anything during the test. It's time consuming. All right. It's up to me to make sure that's true. So don't worry. Everything will be fine. you'll get through this comfortably. All right. All right. All right. But look for my email tomorrow because I will start creating the homework assignments. So I'm going to do the homeworks first, and then I'll do the quizzes. All right. Because the quizzes take a little time to set up, but the homework doesn't take any time at all. So the first homeworks will probably be due, let's say, next Wednesday and Thursday, and then the quizzes will be due maybe Friday and Saturday, and then there'll be another project. The project I can't give you until after next Thursday. All right. So that project will be something you'll do over the weekend before the test, but it'll also prepare you for the test too. So it's not going to be like this useless thing that you'll be doing. All right. Han, you don't believe a word I'm saying.
I believe you.
All right, good. All right. All right, guys. So have a good weekend. Again, nothing due next Tuesday because, again, I haven't assigned anything yet, but look out for the first email tomorrow, probably later in the day. All right. And I'll give you some idea of when the homework's going to be due. All right. Take care. See you.
All right, you too. Have a good night.
You too. All right. Bye.
Good night.
Bye.